In this lesson, we're going to be looking at angle properties of regular polygons. And what we're going to cover includes describe and illustrate angle properties of regular polygons, explain using examples why a given property does or does not apply to certain polygons, identify and explain an application of the properties of polygons in construction, industrial, commercial, domestic, and artistic contexts, and solve a contextual problem that involves the application of the properties of polygons. So we're going to start with explaining what exactly is a regular polygon. A regular polygon is a closed figure with 3 or more straight sides and equal side and angle measurements. So if it has 3 sides, all of them are equal in length, all of the angles are equal in length, there will be 3 angles there. If we have something with 5 sides, all of the sides will be equal in length, and all the angles, all 5 angles, will be equal in length. If we have something that has 20 sides and 20 angles, all of those sides and all of those angles will also be equal to each other. So some of the more common ones we might see include a regular hexagon. A regular hexagon is a closed figure with 6 straight sides and equal side and angle measurements. Then we have a regular pentagon. A pentagon is a closed figure with 5 sides. So a regular pentagon is one with 5 straight sides and equal in side measurements. And then what you might see regularly as a stop sign is an octagon. A regular octagon would be a closed figure with 8 straight sides and equal side and angle measurements. We have this table here. The first row in this table we actually determined from the last video. And that's, if you have the number of sides is 4, what you have is a quadrilateral. We have a diagram of a quadrilateral. We see that there's one diagonal drawn in that splits our quadrilateral into 2 separate triangles. We see there are 2 triangles formed, and we know that for any quadrilateral, the sum of the angles in that quadrilateral is going to always add up to 360 degrees. Notice that when we're making these triangles as well, that they do not ever cross over each other. So if we have a 5-sided figure, a pentagon, we can see that we can create 3 triangles, and the sum of the angles in any pentagon, if you were to take a protractor to a pentagon, you would find that they always add up to 540 degrees. The number of sides, if the number of sides is 6, then we have a hexagon. And in a hexagon, you can see that there can be 4 triangles formed. The sum of the angles in a hexagon is going to be equal to 720 degrees. So basically what we're discovering here is that for the sum of the angles in any regular polygon, any polygon can be made by combining triangles. And the number of triangles that combine to make any polygon is always going to be 2 less than the number of sides in that polygon. So let's just quickly go back and look at our table again. In the 4-sided figure, we were able to create 2 triangles, as long as none of our vertices in our triangles overlap. In the 5-sided figure, the pentagon, we created 3 triangles. And in the 6-sided object, the hexagon, we created 4 triangles. So it is true in all 3 of these cases that the number of triangles formed is 2 less than the number of angles or number of sides in each of the shapes. And if we want to calculate what exactly the sum of those angles is, we can use the formula that's given here. S, which stands for the sum of the angles, is equal to 180 times n minus 2, where n is the number of sides in a polygon. If n is the number of sides in that polygon, then that means the number of triangles is equal to n minus 2. And what we're actually seeing here is that any polygon can be made up of triangles, and every triangle has 180 degrees. So if we add two triangles together like we do in a quadrilateral, we're going to get two 180-degree triangles combined, which adds up to 360. 180 plus 180 is 360. If you have a pentagon, we have three triangles, and each of those triangles is 180 degrees, and the angle is measured to 180 degrees in total. And there are three triangles, so 3 times 180 will give us 540, and so on. So we're going to look at calculating the sum of angles in a regular octagon. So an octagon is much like a stop sign again. So a stop sign has 8 sides. Oct stands for 8. So our formula is S, which is the sum of the angles, is equal to 180 times n minus 2. And in an octagon with 8 sides, that would be 180 times 8 minus 2. And 8 minus 2, using order of operations, can be reduced to 6. So we have the sum of the angles in an octagon is 180 times 6. And if you multiply 180 by 6 on your calculator, you're going to see that it's equal to 1080 degrees. So how about the measure of each angle in a regular polygon? So we know what the sum of the angles is. Now we're going to look at what does each individual angle actually equal. In a regular polygon, the interior angles are always equal. So to calculate the measure of each individual angle, we then divide the sum of the angles by the number of angles. Because if all of them are equal, they're divided up evenly. The formula that represents this relationship is m, which stands for the measure of the angle, is equal to 180 times n minus 2, all divided by n. You'll notice that the numerator of our fraction here, the top part of our fraction, is equal to 180 times n minus 2, which is exactly the same as the formula we use to calculate the sum of all the angles in a triangle. And n being the number of angles in the polygon, we divide the total sum of the angles by the number of angles, and that'll give us the number of angles in the polygon. Or, sorry, the measure of each angle in the polygon. So, for example, we're going to find the measure of the interior angles in each of the following regular polygons. We have a square, which is a 4-sided figure, but it has all sides equal and all angles equal, which is the stipulation for a regular polygon. Then the next we have is a regular pentagon, a regular hexagon, and finally a regular octagon. So if we want to find the measure of the interior angles, I can extend my table to look like this. In a square, we know that there are 4 angles. The square has 4 different vertices, so there's 4 angles. And we know that the sum of our angles, because we've already calculated that, is equal to 360 degrees. In a pentagon, there are 5 angles, and those 5 angles add up to 540 degrees. In a hexagon, there are 6 angles, and the sum of those 6 angles is 720 degrees. Finally, for our example, although we can go much further beyond this, we have an octagon. And an octagon is an 8-sided figure, so it has 8 angles. And the sum of the angles we just calculated a minute ago is 1080 degrees for an octagon. So I'm going to show the measurement, or the calculation, sorry, for the measurement for a square. And the same calculations will be performed to find the sum for a pentagon, sorry, the measure for a pentagon, a hexagon, or an octagon. So for our square, we're going to use the formula that we provided a minute ago for m. M is equal to 180 times n minus 2. 180 times n minus 2 being the sum of all the angles in a polygon. So 180 times n minus 2 divided by n, which is the number of angles that are present in the polygon. In this case, n is going to be equal to 4 because there are 4 angles in a square. So what I'm going to do now is substitute 4 in place of n in my formula. So now I have 180 times 4 minus 2 divided by 4. Every time I see an n, I replace it with the number 4. 180 times 4 minus 2, or 4, reduces to 180 times 2 divided by 4. 180 times 2 divided by 4 is 360 divided by 4. And 360 divided by 4 is equal to 90 degrees. So I'm going to put that in my table. So for a square, the measure of each interior angle is going to be 90 degrees. We can perform the exact same calculations on our pentagon, our hexagon, and our octagon. The only thing that'll change is the value for n. And when we do that, here are the numbers we get. For a pentagon, the sum of the angles is 540 degrees. The number of angles is 5, so we perform the calculation 540 degrees divided by 5, and that works out to 108 degrees. For a hexagon, the sum of the angles is 720 degrees, and there are 6 angles, so the measure of each interior angle is going to be 120 degrees. Lastly, again, for our table, we have an octagon, which has 8 angles, and the sum of the angles is 1,080 degrees. So if we take 1,080 divided by the number of sides, number of angles in the octagon, which is 8, we're going to get that each interior angle in an octagon should measure 135 degrees. So to summarize this, a regular polygon has all sides and all angles equal to each other. Any regular polygon can be created by combining triangles. The number of triangles is always going to be 2 less than the number of angles in the polygon. And the formula for finding the sum of the angles in a regular polygon, S is equal to 180 times n minus 2. And again, n is the number of angles in that polygon. And once we know the sum of all the angles in any polygon, we'd like to know what the measure of each interior angle in that regular polygon will be equal to. So we use the second formula, m is equal to 180 times n minus 2, all divided by n.